FITSA seminar today. Our speaker is Erik Peterson here from Duke University Cosmology Group, Cosmology. So Erik did his bachelor's at Notre Dame, Indiana, with Peter Garnavich, and then moved to Durham, North Carolina, to join Dan Skolnick group of supernova cosmology. He has been working in Pantheon. You may have heard of Pantheon with these new DESI papers out that there's some tension with Pantheon, with DES, with Union. Oh, sorry, no, I'm not gonna say anything else. So he has been part of the Pantheon team, in particular working on peculiar velocities, measuring, improving redshifts and getting the peculiar velocity information from that. And more recently working on 1As in the near infrared in a program called DEHVILS. And there have been a couple of papers led by Erik. You are basically Dan, you are the leader of this program. And I guess you will talk about all this.
Yeah, you just gave my presentation.
Excellent. Thank you very much. So,
Okay, hola a todos. Voy a presentar en inglés, pero estaba pensando que debo presentar en español, porque estoy en España, ¿no? Pero me di cuenta que no sé cómo se dice supernova cosmology o scatter on the Hubble diagram, entonces tengo que presentar en inglés. ¿Está bien?
We don't know either.
Okay, yeah, so I'm Erik Peterson. I'm a fifth-year PhD student at Duke, and I will be graduating next year, early next year. And I'm hoping to tell you a little story about what I've been up to the past 5 years and what I'm hoping to continue working on in the future. So first, I'm sure most of you have seen this figure here, but if you plot velocities versus distances, you can understand and characterize the expansion of the universe very easily. And here you can see, just by plotting these astronomical objects, you can obtain the Hubble constant. This was done by Edwin Hubble in order to provide expansion or evidence for the expansion of the universe. ¿Todo está bien? So this is what a more modern Hubble diagram looks like. And as Luis told us, this is from actually the Pantheon Plus survey, which I'm a part of. And instead of that initial Hubble diagram by Edwin Hubble, this Hubble diagram goes way further in redshift. The first Hubble diagram only went out to about here. And what we can see, though, is that it boils down to basically the same thing. You have distances on one axis and velocities on the other axis. In this case, we have distance modulus and redshift. And then what we do is we fit a cosmology to these data, and we find how well do these fit to those data. And so we take the residual here from with the fit to the data in order to obtain what we call Hubble residuals here in this lower panel. So I'll talk about the Hubble diagram a lot today. In order to actually construct it, I want to give a very brief review of these cosmological tools that we use to construct these Hubble diagrams. The first being a Type Ia supernova. And this is an example image that my team took with the DEHVILS survey, where you can see the supernova right there, indicated by the green arrow, among its host galaxy, and it can be almost as bright as a full galaxy on its own. And we estimate approximately 1 supernova per galaxy per 100 years. And then I'll briefly mention why magnitudes are important, and then redshifts as well. So first, that Type Ia supernova. This is an example scenario of a Type Ia supernova where it reaches its critical mass, the Chandrasekhar mass limit, and then it can no longer remain stable against gravity, and then it explodes. In this case, the diagram I've given you there is a single progenitor scenario, and we're not actually sure as a supernova community if it's a single progenitor or a double degenerate scenario but that doesn't seem to impact cosmology all that much. We're still looking into this, though. The reason why supernovae are so important is because we understand them to be standardizable candles. The principle of a standard candle is if we know how bright an object intrinsically is, and if we compare that to how bright an object appears to us, then we can relate those two in order to obtain a distance. And in astronomical terms, if we can get the apparent magnitude and then relate that to the absolute magnitude, we can get our distance modulus there. Now, that's the principle of a standard candle, but supernovae are standardizable. And that's because we have to correct for a few empirical correlations, such as how quickly the supernova fades in brightness or the supernova color as well. So I'll talk about focusing on that standardization a lot today. As for redshifts, you all know what a redshift is, but I want to emphasize that redshifts can come from both motions as well as expansion. We saw those expansion redshifts on the Hubble diagram, but there's also motions. You can see that cartoon, the simple cartoon there, where there's a Doppler redshift. And then what we do is, as Luis mentioned again, is we study peculiar velocities, where these are the motions due to gravity or other things. And we build maps like this in order to map out the matter in the universe in order to actually study the redshift itself, the cosmological redshift itself. So you may have already been thinking, why do we actually care about improving the Hubble diagram itself? And there are a number of reasons, one of which being the fact that the Hubble tension remains, it persists, right? And this is the fact that in early time, these are early time measurements of the Hubble constant, the current expansion rate of the universe. These were measured by taking a look at close characteristics of the universe at early time and propagating that out to a measurement of the Hubble constant to time measurements of the Hubble constant, such as from supernovae. Those are highly discrepant. And so the questions remain to this day that potentially our questions are, did early time or did late time mess up? Or is potentially our standard model for cosmology, flat lambda CDM, is that incorrect? So these questions remain. And understanding supernovae on the Hubble diagram is important for this. Another reason that we've hinted at already are these DESI results from the dark energy spectroscopic instrument. These came out just a month ago. And what you can see here, if you plot various cosmological parameters here, you have the dark energy equation of state parameter W versus omega matter, the energy density of matter in the universe. If you plot just the DESI results themselves in blue, you can see it's not the most constrained to cosmology. But then if you add in cosmic microwave background results, that can help constrain your cosmology. But then further, supernovae, which are orthogonal to those CMB results, you can see that you're able to constrain your cosmology really well down to this orange contour here, that very small one. And what we see on that plot is that W is consistent with a cosmological constant. Okay. However, if you look on this right plot here, if you assume potentially an evolving cosmology with dark energy, you have a WA, W naught model, you can see that depending on which supernova sample you use, you're potentially more and more discrepant with a flat lambda CDM. That W naught or WA is away from zero potentially. And so even just looking at these various supernova samples, you can get variant tensions potentially with cosmologies. And even further, some of these samples, so Pantheon Plus, the one I work on, and Union 3, and then from the dark energy survey, these samples overlap a lot in ways, and just how we're treating our systematics can result in large differences in cosmology. So this is a really important question for today. All right, so I've motivated why we're looking at the Hubble diagram, and this is how we're actually going to do that. So focusing first on that y-axis, what we see from this Hubble diagram is that approximately there are over 2,000 Type Ia supernovae used for cosmology in the optical. And what we see is that after accounting for measurement noise that we expect in these Hubble residuals, we see that there's about 0.15 magnitudes of scatter remaining on the Hubble diagram in the y-axis. And we call this intrinsic variation. And if we were to see a bias with respect to redshift, or a slope here in these Hubble residuals, we'd know that there's a cosmological bias that we don't see right now. But what we do see is this intrinsic variation, and we want to understand what that's coming from. And so what I'll tell you we can do, and what we've been working on this whole week and further, is that we can look to the near infrared for a number of reasons. One, it's to improve the precision, that scatter on the Hubble diagram, as well as if we look to the near infrared, we can learn things about the optical better too. So one title that's used often is this fact that Type Ia supernovae are excellent standard candles in the near infrared rather than standardizable. So there's this lore about supernovae in the near infrared. And what you can see is if you look to this abstract and you see the scatter that they obtain when looking at near infrared supernovae, with smaller scatter, a single near infrared supernova can be as useful as two optical supernovae. Another thing that we can take advantage of in the near infrared, so that was improving precision. We can also try to take advantage, as I briefly mentioned, of the fact that near infrared light is less affected by dust. So this cartoon here describes how near infrared light is going to be able to pass through an optical cloud or a dust cloud, whereas that optical light is more likely to scatter there. And so if we see various systematics in the optical that are due to dust, if we look in the near infrared, we can learn if that truly is the case or if not. We can also learn more about the optical itself if we look to the near infrared. As for the other axis, we look to use peculiar velocities to improve redshifts. And by peculiar velocities, for those who don't know, these are going to be all motions, this is how we define it, all motions of galaxies that are not due to the expansion of the universe. Where this is our scenario, this would be the ideal situation for supernova cosmology. If we were here in the Milky Way, we observe this target galaxy with its recession velocity, we can characterize the expansion of the universe easily from that. But what we really see is we have these extra components to these velocities. There's a peculiar velocity potentially, which I'll break down later, as well as our own motion with respect to the cosmic microwave background as well. So on this axis of the Hubble diagram, this is a mock Hubble diagram where color is independent knowledge and try to correct for that on the Hubble diagram in order to characterize that expansion redshift on its own. I also forgot to mention, you're welcome to ask questions during the presentation if you like. Okay, so looking at this quantitatively, do you have a question already, Joel? Or is it you're stretching? Okay. If you look at this quantitatively, and we have to focus on peculiar velocities at low redshift, because the farther that you look, the more the expansion velocity will dominate. Whereas if you look here at low redshift, the peculiar velocity will make up a large percentage of that overall redshift. And it can make up approximately even 10% of the cosmological redshift on its own at very low redshift. All right, so how are we going to improve the Hubble diagram? We'll look to the near infrared to try to get the better distance measurements, and then we'll try to obtain better redshift measurements by correcting for peculiar velocities. And specifically, I'll get into how we can use galaxy group information to do this. So first, we're going to look to the near infrared. One of the largest systematics today is actually understanding what is the cause of that intrinsic variation that I introduced. And what we can do to try to understand what is the cause of this intrinsic variation is look to see if we can correlate this with other measurables, and see if then we can learn more about what this actual intrinsic variation is. And so one of the most obvious ones that was done in 2010 is we can plot Hubble residuals as a function of host galaxy mass. And what we see is that there's actually a correlation there. That you can see there's approximately 0.1 magnitudes of a mass step there. That's what it's called, the mass step. This correlation between Hubble residuals and the mass of galaxies hosting supernovae. And you may think that this looks like a little bit of a blob here, but we've seen this across many studies that this mass step exists. And we still don't know what is the cause of the mass step. And the fact that there is a correlation between these Hubble residuals and a measurable like a host galaxy mass means that there's science there, that we're able to understand potentially what is the cause of this intrinsic variation if we can solve what this mass step is about. And so what I do, and I've done in my work, is try to look at a few different models for intrinsic variations. So there's two I'm going to introduce today, one being achromatic and another being chromatic, where this can tell us information about, so these are models for intrinsic variation, and these might have hypotheses for what the mass step could be. So first, for that achromatic model, what I mean is that intrinsic variation is not a function of color or wavelength, whereas this intrinsic variation is the opposite. It is a function of color wavelength. Now, these are two models on kind of the two extremes of what intrinsic variation can be. And we've talked this week about how it's most likely something in between. But to look at two ends of the spectrum, that's what I'm going to do with my analysis. What this would mean for intrinsic variation, if this achromatic model is more correct, is that potentially there's an inherent luminosity difference between supernovae. This would be tough. Whereas if this chromatic model, an explanation could be that the luminosity difference is due to dust. And so then what this would mean for the mass step, if this achromatic model is more likely, it could be progenitor-based. For example, a supernova that's brighter might have a different age. Its progenitor might have a different age. That could be related to the age of the galaxy, which could be related to the mass of the galaxy. There's other examples that could be progenitor-based. Whereas this dust-based model, potentially dust itself, the characteristics of dust could be different in different kinds of galaxies. And that could result in the mass step that we see. So these are two potential explanations. So this is what I set out to do, is to try, well, what we do see is we see a mass step in the optical. If we see a mass step in the near infrared, potentially that progenitor-based model is more likely, whereas the opposite, if we don't see the mass step, potentially that near infrared or that dust-based model is more likely. All right, so we've stepped through this story a little bit here, that we have our intrinsic scatter, potentially it's due to dust. We'll look to the near infrared for this mass step to try to see if it is. And the truth of this is going to be able to tell us more about Type Ia supernovae. And I think that we really need to understand this, understand supernovae themselves a lot more before the Roman Space Telescope is launched, which I'm very excited to work on in the future. The Roman Space Telescope being NASA's next flagship mission, launching this decade, and it will be observing in the near infrared. It'll observe out to a redshift of 3, and so it'll obtain rest frame near infrared data out to about 0.6, according to my estimations. And Roman will require an anchor sample, number one, so that we can actually compare very low redshift out to higher redshift on our Hubble diagram in order to constrain cosmology. And we also we still have time to modify the observing strategy for Roman, but we need to optimize this, and we can only do so if we understand supernovae as well as we can beforehand. One problem, however, is the fact that the sample of supernovae that have been observed in the near infrared is approximately less than 300. And then this number is a little bit up for debate. We've been talking about this, but of light curves that have already been published that are usable for cosmology, in a sense, however you want to define that, it's approximately 300, compared to, if you remember, over approximately 2,000 that are observed in the optical. And there are many reasons for this, but this is the status as of now. Of these 300 light curves, many of them are not well sampled at all. So if you look at an example, Luis is laughing. If you look at an example, and I'm going to, if you look at an example of supernova light curve in the optical, here, you have your brightness as a function of time, and this is from Foundation that's used for cosmology. You see approximately 5 to 6 observations in 4 different optical bands. If I compare this to an example light curve in the near infrared, you may be able to guess, some of you supernova folk, which light curves I'm going to show. For example, maybe from Sweet Spot, you see that this is an example light curve here where there's 1 observation in 2 bands, or potentially even 1 band with 3 observations. And actually trying to constrain these light curves is difficult, definitely with near infrared information alone, for sure. So there are far fewer supernovae observed in the near infrared, and of those supernovae observed, oftentimes those light curves are not well sampled at all. And even the ones that have many observations, they're constrained to very small portions of the light curve, potentially, not near the peak. And so this is where we come in, where I've come in with our own near-infrared supernova analysis using DEHVILS. And DEHVILS being the dark energy, H0, and peculiar velocities using infrared light from supernovae, which I know is a difficult acronym. It's for the Duke Blue Devils. That's what we are. And I'll tell you, I did not make the acronym. So, but we use the United Kingdom Infrared Telescope, UCURT, on Mauna Kea. For this near infrared side, this y-axis of the Hubble diagram, I'm going to talk about 2 papers, primarily from DEHVILS. One of which is our data release paper, and then the other one I call the DEHVILS in the details. So where we dive into what's actually going on with DEHVILS. So you may be able to guess what some of the goals of DEHVILS are. Number one, it's to try to boost the sample of near infrared light curves. That's a first order one. And then we want to understand near infrared supernovae better, as well as supernovae on their own better. And then we want to be a large chunk of that Roman Space Telescope's anchor sample. And I want to emphasize there have been previous near infrared studies, but the light curve coverage has been sparse. So we want to constrain a large chunk of that overall light curve, and we try to do so with some good quality. This is the current status of DEHVILS, where 83 supernova light curves have already been published, all of which have spectroscopic redshifts, and they are all spectroscopically confirmed Type Ia supernovae, and we're averaging approximately 6 observations in all 3 near-infrared bands of Y, J, and H. And we reach a redshift range of out to about 0.1 in redshift. This is a picture of me on the top of Mauna Kea in front of the telescope that we've been using, UCURT, which it was just such a fun experience to be able to go to this telescope. So comparing DEHVILS to other published supernova samples that are out there, you can see that DEHVILS looks really good. So if you just take a few different cuts, a few simple cuts, ensuring that you're looking at type Ia normal supernovae, you have at least 3 near-infrared bands, as well as at least 1 near-infrared epoch near the peak. And you compare that to other supernova samples in the near-infrared that have been used primarily. There are others, but CSP and CFA here are large ones. DEHVILS compares really well. It's approximately 40% of this sample size that I've analyzed. As for the data reduction itself, this is our principle, how we obtain a science image here with the supernova there. Then we obtain a template image, either more than a year after the first observation or from the archive, in order to subtract this template image from the science image to obtain a differenced image. We do that for all of these in order to construct our light curves. And this is an example, very good light curve from DEHVILS, where we have 6 to 7 epochs in all 3 of these bands. Okay, so I introduced to you the DEHVILS survey. Now back to our question. If we look for this near-infrared mass step, this could tell us about whether or not this dust-based model is more likely. But I'll tell you that this test has been attempted before. If you take a look at this figure, where it has the size of the mass step as a function of bandpass, you'll see that if you look at the optical wavelengths here to the near-infrared, you see their data in these points, as well as they compare to a dust-based simulation. Now, this dust-based simulation goes as what we might expect, where we see the mass step in the optical, and as you step to near-infrared wavelengths, you see it go away. So if it is a dust-based simulation, that's what we might expect. And what they claim as a part of this work, this recent work, is that dust cannot be the cause of the mass step because their data do not fit to the simulation. So they rule out this dust-based model. But again, I want to say we want to take a closer look. If I remind you very quickly of this mass step plot, I mentioned that the size of the mass step that we've seen in this plot and then many future studies, the magnitude of the mass step is approximately 0.1 magnitudes in the optical, 0.1 magnitudes in the optical. But if we look at this figure again, you see that this dust-based simulation is a magnitude of the mass step of even larger than 0.2 in magnitude. And so what we say is potentially, we're not sure how they got this simulation to have such a large mass step in the optical. But what I want to do is provide a more reasonable set of simulations in order to compare their data, as well as the near-infrared data from DEHVILS too as well. And so we construct a more reasonable mass step right here with these simulations. So in orange, you can see the dust-based model, and you can see that it follows that same qualitative trend where it has a more likely, as we imagine, in the optical here, this mass step being on that level of 0.1 magnitudes. And we see that trend. Whereas we also plot this simulation, the progenitor-based simulation, with that mass step, as we might expect, being achromatic, not a function of color there. Okay, so in the next slide, I'm going to plot their data. I choose the orange or the blue circles here, which are the combined, it's the total sample. I use the blue circles and compare their data to my, what I believe to be more reasonable simulations on this next plot. And this is what you can see. You can see that their data is in red, with the values in the dotted lines with 1 sigma uncertainties on either side. And then those same simulations I plotted on the last plot in orange and blue again. So if you see the size of the mass step versus wavelength here, rather than allocating equal width per band pass, you can see that neither simulation can be ruled out by those data. Right? So they fall within 1 sigma of each of these data points. And so what we conclude as a part of this is that it's more difficult to differentiate between these intrinsic variation models here. And so then what I do is I also take a look at the DEHVILS data, and you can see again that as for this smaller sample size, and we're working to increase the sample size now, with this size of a sample size, the constraint on the mass step is very limited. And so I plot the same thing for my data on the same plot in the next slide. And you can see in green, maybe you can't see it so well, but again, neither simulation can be ruled out truly by way of these because of these data, right? So that's a conclusion of ours here. We take a look at two different tests to see if we can differentiate between these two intrinsic variation models, one of which we plot Hubble residuals as a function in the optical versus Hubble residuals in the near infrared. From that achromatic progenitor-based model, we obtain this slope using an orthogonal distance regression model here. And then we see this dust-based model with a larger slope, where it's more constrained on the x-axis. And then we compare that to our data. And what we see is that the slope from the data falls right in between these two models. And so we're unable to, again, in this situation, differentiate between the two. We see that similar story. However, I'm excited and we're excited about the future here, that we, with a larger sample size, as well as with Roman data, we're going to be able to answer these questions, we believe. What you can see is what I've estimated is that approximately 300 Type Ia supernovae will be discovered with rest frame near infrared data from Roman. And I'm even more excited that this is what a typical supernova light curve in the near infrared will look like with Roman, with just unbelievable cadence. You saw the DEHVILS supernova light curves, unbelievable cadence and great precision there. And so in order to prepare for, I'm going to say again, this Roman survey, we need to understand these near infrared supernovae in order to optimize the Roman survey strategy. Okay, so that was the near infrared. Does anybody want to ask any questions now or wait till the end? Yeah.
Yeah, thank you very much. So there is, you mentioned at some point that you correct for the peculiar velocities using local groups.
Yes.
Local universe group, galaxy groups. So how does this work exactly?
Yeah. I'll talk about that this next chunk. Yeah.
Okay.
Yeah. Yeah. Any questions about the near infrared though first? Yeah, Alex.
Yeah, very nice. So I have a question about how you measure the mass gap.
Yeah.
Specifically, do you assume that there's an intensity scatter, and how would that affect the significance of the measurement of the magnitude of the mass gap?
Yeah, so it's a very rudimentary method, how we calculate this mass step, but this is from the Hubble residuals. We basically do a weighted mean on either side of the mass step location just to see if there's a difference in that average on either side. It's very rudimentary, but that's what we've been working with.
So the intrinsic scatter is simply.
Well, so
you make the average.
So the intrinsic scatter is still present. It's still on this plot. You could see that intrinsic scatter there. We're not accounting for that in the mass step plot. Do you want to add anything to that, Luis?
No, I mean, that's the mass step. It's very rudimentary, as you said,
Yeah.
because it's just dividing at some point and measuring, doing averages there. But there have been more, I would say, elaborated statistical methods that try to, instead of just a mass, fit something there, and all of them kind of found some difference.
Yeah.
But it's easy to, usually what this is, when this is included in the standardization, is just another term in the correction that has to do with this. So
Yeah.
basically the high mass beam gets an extra correction. So you put that in the same level. But it's not super. I mean, as you said, this is it looks like a cloud. And when you start doing populations here, you see that there's clearly some difference. Some population on the right that is not present on the left, and that makes the thing to look a bit like this.
Yeah.
But yeah, there's a lot of things to look at. It's not.
about the
Okay.
Yeah, I wanted to ask if there is any relation for a given mass with respect to the location of the supernova in the galaxy. If they are in the outer parts, inner parts, has that been checked?
Yeah, that's definitely something that people have looked into, as well as looking at correlations between like global and local properties of the supernova itself. And I don't think that there is a correlation necessarily if you're accounting for the galaxy light correctly, a correlation between how far it is from the center of the galaxy. Yeah. But it's very difficult in the near infrared to correctly account for the light from the galaxy. Yeah. Okay, great. So now we'll get to the peculiar velocities and how we correct for it. So to return back, this is our plan that we obtain independent knowledge of the peculiar velocities from various models, and we use that as a correction to the redshift itself in order to correct the redshift to be a better cosmological redshift itself. Okay, and for this section, I'm going to talk about specifically one paper and then some ongoing work that's going further into the peculiar velocities. So I showed you this slide again before, detailing the ideal situation where we study the cosmological motion, and now we're actually going to break down this peculiar velocity into components. And the idea is if we can correct out this non-cosmological motion, those redshifts will be more accurate. So if we break it down into components, you have our own motion with respect to the cosmic microwave background, and then you have some different scales here. A small scale motion, this intermediate scale, and a larger scale motion in this cartoon here. And what I'm going to focus on is primarily this small scale motion as well as the intermediate scale motion and what that means on the Hubble diagram. What you can see from the small scale motion, which we call galaxy group motions, is these are motions within a galaxy group. And different catalogs or different studies have different definitions for what a group is. And what we do is we take a look at how well can we do looking at these various group catalogs. How well are they defined? And these are on the scales of approximately less than 10⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻ motion, it's very simple to begin with, is we obtain a galaxy group velocity average, and we deem that to be a more precise cosmological redshift. What we do then is we also take a look at coherent flow motion, which is also understood as bulk flow motion. These are motions of the groups themselves towards larger scale attractors. And these are on the level of tens of h⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻ these peculiar velocity models oftentimes make use of mass density or redshifts as well. And these are what the maps look like oftentimes. So you can see that if you can map out, again, the structure in the universe, you can predict how much the motion will be due to peculiar velocities, and then you can account for that itself. Okay. So then we put it all together where we have a number of different group catalogs. Those are defined oftentimes by velocity and distance association. You can also do a friend of friends algorithm. And then we also have various coherent flow. These are the intermediate scale motions. These are defined by using density fields. Oftentimes, this is from 2m++, for example, as well as direct measurements of peculiar velocities themselves from redshifts. Cosmic Flows 3 is an example survey that does that. And what we do is we test these corrections on Pantheon Plus data. And we do so by looking to see which model can reduce the most scatter in terms of chi-squared on the Hubble diagram. And again, I want to remind you, we have to focus our analysis at low redshift. That's where peculiar velocities are important. So we cut down the supernova Hubble diagram down to a sample of 584 supernovae at less than Z of 0.08. First, I'm going to talk about the group corrections very briefly, and then the coherent flow motions. One of the first findings that we had from this group, the galaxy group analysis, is that of these 485 or 584 low redshift supernovae, only 174 were found to be in any of the group catalogs we analyzed. So only 30% were assigned to groups. And this led to a question, hey, are supernovae not in groups? Are only 30% of them actually in groups? Or have these groups just not been defined? And so this has been a motivating question for some of my ongoing work to try to answer this question. And as we see, this decreases, the galaxy groups decrease as a function of redshift, perhaps because they just haven't been defined. Okay, so this is the result slide for the galaxy group, or for the peculiar velocities analysis. What you can see here is this is reduction of scatter as a function of various coherent flow models. And if you compare the unfilled points with the filled points, you can see that's accounting for galaxy group motion. Okay, and what we see is that just by modifying 174 supernovae of this sample size of 584, you get large reductions in this chi-squared value of about 50 to even 100. So if you compare along this x-axis of the unfilled points to the filled points everywhere, where you're accounting for peculiar velocities from galaxy groups, you're reducing scatter on the Hubble diagram. I know it's not all about reducing scatter on the Hubble diagram, but this is a good test as well. Okay, so if you look at coherent flow motions, if you do compare along the x-axis, you see that some of these models do better than others. You see that primarily these 2M++ models do well at reducing scatter, and 2MRS as well, whereas some of these models, the Cosmic Flows 3.1 and this Virgo, the simple model, those don't do as well at reducing scatter on the Hubble diagram. But we can see that doing so will reduce it overall. And then what we noticed is that this is not actually going to solve our Hubble tension. There was a hypothesis out there in the literature that if you do correctly account for these motions, it could solve it, but we don't see that. We see that if you are including peculiar velocities, these ones that we see are valuable, H0 is actually shifted up by 0.4 kilometers per second per megaparsec. If you don't use a coherent flow model at all, right? So if you look at this on our Hubble tension plot, this small one, there's many other points on here as well. You can see that the value is shifted up. It's further away. Yes.
So thank you for showing how it works. So
Yeah.
you said that you have groups, galaxy
Yeah.
groups. So by then, averaging out, of course, you can measure better the distances.
Exactly.
If you know that the galaxy is this group, you can have a better measurement for the distance.
Yes.
However, the group is also giving another information about what is the velocity dispersion.
Yes.
Do you use this as an uncertainty term? Because you have detected supernova, you have detected a galaxy, but maybe you don't have redshift for this galaxy, for the group.
Yeah.
So do you account for also the velocity dispersion per group?
I mean, that's going to be some ongoing work that we're working on, but we do focus right now. It's again simple on the x-axis for the redshift. So we're using the redshift information in the velocities. Yeah.
However, the peculiar velocity term
Yes.
for each galaxy
They're highly uncertain. Yes.
depends also. You improve on the distance by doing that because you know where the galaxy cluster is. The velocity you don't improve necessarily because, for example, the most blue-shifted galaxy towards us
Yes.
is in Virgo cluster.
Yes.
Its velocity towards us is comparable to the recession velocity of the Virgo cluster itself.
Yeah.
So this is an uncertainty term that you should put in its distance in the Virgo cluster, depending on the position of the galaxy and look how close to the center it is.
Yeah.
This is going to make the uncertainties in specific groups, in the distances, in the velocities, way larger than the typical velocity, peculiar velocity of the galaxy. So this is an uncertainty term that probably is going to make some of these errors so large that are going to be consistent.
Yeah.
You're not going to have any systematic trend because the asset is going to be very large in this region.
Yeah.
That's why I'm asking if you use this term, because it might be very important in these clusters, and this is where you have massive clusters with high velocities, where you have many galaxies and many supernovae.
Yeah. No, so I mean, for the galaxy group work, that's on really small scales, and so they don't have super large velocity dispersions there on the smallest of scales. But as we do step into bigger and larger scale motions, we do have to account for that. Yeah. Were you going to say more?
I was going to say that the distance measure is independent of it's in a galaxy cluster or in a big galaxy. So it has nothing to do. It's just the x-axis, but may change, and could include some uncertainty there. But the assumption on the distance measurement has nothing to do with the fact that it's in a cluster or not. Right? And actually, the thing or the assumption in all this business is that this is low redshift, but what you are assuming is that this capital M is the same everywhere. There may be some evolution, but we have not found that. But you could forget about low redshift, go to high redshift, and there's no peculiar velocities, and the distance measure is independent on which redshift you are. It's just apparent magnitude, assuming an absolute magnitude that gives you mu with some corrections. Okay, but this is only. I mean, I agree with you that you may consider this scatter or the variance in these velocities, but this will go to the x-axis only, not in the y. So I don't see, and I'm not sure if this is what you suggested, adding this as an uncertainty in the y-axis, because this is totally independent.
Not in the y-axis. Yes, that was my mistake, because I use other kinds of distance measurements, not supernova.
Yeah.
But the uncertainty in the velocity for a given supernova event is going to have the galaxies, its own galaxies, which can be even higher than the recession velocity of the group itself.
Yeah, I agree.
In some extreme cases.
Yeah.
In some extreme cases.
Yeah. No.
So as an uncertainty term, it should be used per galaxy group. In a Virgo cluster, if you include it, it's going to be next axis like that.
Yeah.
Passing at minus velocities, right?
No, we're working on that too. Yes. Okay, so the last few things that I'll say, this could take it even further into F sigma 8. There's ongoing work here as well, and that's where kind of the future of peculiar velocity work will go as well. And then very briefly, this ongoing work, I mentioned this question that are these galaxies not in groups, or have those groups just not been defined? We've obtained some data with the AATs, the Anglo-Australian Telescope's spectrograph. It's a fiber spectrograph, AA omega, and observed that approximately 80% of the new data that we took for supernova host galaxies that were not defined in groups previously, we found them to be in groups. And so we want to motivate future spectroscopic surveys to hopefully find more galaxy groups as well. And so what you can see is, again, we're trying to reduce scatter in terms of redshift here by using the group redshift rather than the individual redshift of the supernova. I'm adding in Pantheon Plus data as well into this analysis to dive further into galaxy group work. And then we're also going to include some analysis with simulations, specifically from Uchu this work. So we're really excited about that. And I hope you learned today more about how we can improve the Hubble diagram scatter on both axes. In the near infrared, there's more work to be done in our group, which we might call the Saints group here. We're working on that in the near infrared. And then this galaxy group, peculiar velocity work, we say that more galaxy groups need to be defined. but we're excited about that. So thank you so much for having me.
Thank you very much, Erik.
Any further questions? Yeah, Tomas.
Yeah, so maybe for your Jewish whoever knows, you essentially need redshift to define the galaxy group, right?
Yeah.
But what about like DESI? Would DESI get, for example?
Yeah, no, we're definitely going to look at DESI to see if there's more information there, but there needs to be. I'm not in the business of defining the group. I guess I am some, yeah.
You are, yeah.
In at least the coherent flow models, I'm not in the business yet for that. But yeah, we can use DESI for sure. Yeah.
More questions there?
Yeah, Tomas.
Okay, so I do not quite like understand when you were talking about the achromatic effects. Like, why would a difference in age would just like shift all the magnitude in every wavelength the same direction? Like, does that come from simulations or is it just from theory?
I mean, it's a theoretical explanation. There's many others that could be related to metallicity is another example. But like in principle, if the progenitor age is tied to the brightness, it could also, that could be that could go to age could go to metallicity too, right? If it's tied to the brightness of the galaxy, then the age of the progenitor could be tied to the age of the galaxy, which could be tied to the mass potentially.
I was thinking that maybe a difference in metallicity or whatever.
Yeah.
Affect differently the optical than the infrared. So you
Yeah.
might not affect just like a
Yeah.
lot of shift, but also some slow.
Yeah, it doesn't have to be achromatic. Like it could even be progenitor based and anachromatic. There's some combination for sure. But those are kind of the two extremes, and you might expect in between potentially. Yeah.
Right. Yeah.
In fact, there are many subtypes of type Ia supernovae.
Mm-hmm.
How precise can you distinguish among them? Because the difference in magnitude and maximum can be very large.
Yes, you need to have very detailed and well-sampled light curves oftentimes to do so. There's ongoing work to try to differentiate between peculiar 1As and others just from undersampled supernovae. Some people are trying to do that with machine learning and whatnot. But if you have the more well-sampled your light curve is, the more you can differentiate between a normal type 1A and a different kind, for sure.
But in the case of quite far type Ia supernova, can you distinguish clearly the difference in the spectra, the change, for instance, of the Phillips relationships and so on?
If you go If we go farther and farther in redshift, we can't differentiate perfectly between, definitely. As you go farther in redshift, you can't tell if it's a 91T like is a super Chandrasekhar, we believe. Yeah, it's harder, especially as you go farther and farther, for sure. But what we try to do is we try to account for that bias, and hopefully, if you get enough supernovae, the overall sample will give you the correct cosmology. Yeah. Yeah.
Well, actually, the main contaminants are those that are faint, so at high redshift are not even observed. And actually, we have to apply these bias corrections that you mentioned to recover the population of normal faint objects that we are missing because of the deepness, the depth of our satellites.
Yeah.
It's not a big deal because these are low redshift with spectra. They are very easy to remove. And high redshift, we actually don't see them.
We also apply like cuts on the micro parameters to remove like any weirdo
from photometry, not from.
Yeah.
Any other question? Hungry? Okay, so let's thank again, Erik. See you in the patio. Right?
Thank you.
Ya estamos, Alba.
Thank you.
Now we learn something else. I
Yeah, because you never talk about supernovae.
never thought when I talk, they are not listening. It's good that you.
I'm so happy.